So you've had a Wi-Fi survey done and the report looks good, but something's wrong and you're getting lots of complaints from users about poor performance and dropped connections. Of course, there may be separate network problems that have nothing to do with Wi-Fi, but the fact is, just taking some readings and producing some heat maps doesn't get to the heart of how your Wi-Fi is performing. So did your Wi-Fi survey get to the heart of your Wi-Fi performance, or did it just scratch the surface? I'm going to go through some of the main things that I often see being missed in Wi-Fi surveys. First, I'll give some examples of what's wrong with taking Wi-Fi survey measurements at face value. Then, I'll give a short overview of what Wi-Fi really is. Then, I'll cover three key areas broadly under the headings Client, which is another name for user device, sensitivity and capacity modeling, measurement accuracy and comprehensiveness, and client roaming behavior and design. I'll also provide some background information on how the sensitivity of the client device determines the signal strength that the client sees, and how the amount of useful signal after channel noise, the signal to noise ratio or SNR, affects data rates. Then I'll finish off with a summary of the things you can check for your Wi-Fi survey. So let's look at Wi-Fi surveys and their problems. So let's start by looking at what a Wi-Fi survey is for and get some clarity on the terms used. You'll notice I've listed facts on some slides in this video to help as a reference when revisiting. So a Wi-Fi survey is done as part of a design to optimize the performance of users' devices. Now they're done for three main reasons: to understand the health of your Wi-Fi network, as part of an on-site design or redesign process, or to validate that an install design meets the original design criteria. And for design or redesign jobs, there are three different types of surveys or designs that are done. First, there is the so-called AP on a stick, where an access point, one of the devices that delivers Wi-Fi, is mounted on the tripod so that its coverage pattern and radio or RF characteristics can be measured in all relevant parts of a site. Then there's a hybrid design where some key measurements are taken to help build an accurate design in software. Or there's the desktop design where no physical survey takes place, assumptions are made, and the whole design is built in software. Now, surveys are generally passive, which means you do not interact with the Wi-Fi installation directly, you just measure it. However, you can validate data rates and throughput during a survey by connecting to it. So in this case, it's called an active survey. So here are some of the common misconceptions about Wi-Fi I come across. Wi-Fi is just like wired networking, so you only need to have been on a wired networking course which touches on Wi-Fi to be able to design it. Or the survey engineer just needs to know how to drive the surveying tool and capture the required heat maps. Or access points just need to be set to maximum power. Or you just need to get a strong signal from Wi-Fi access points. Or all you need is a report containing good heat maps to prove that the Wi-Fi is good. So let me start by dispelling the myths. So let's have a look at some of the tools you need to do a Wi-Fi survey. As a starting point, you need some survey and design software which runs on a survey device such as a phone, tablet or laptop. And this in turn connects to a survey instrument which measures the frames coming from the APs and provides the data for the heat maps. Usually the survey instrument is also able to do radio spectrum analysis, which is useful to identify frequency-dependent sources of interference. The survey instrument may also be able to capture the complete messaging between APs and clients on a subset of channels, for which you can do detailed analysis with separate protocol analysis software. You may also be able to capture a copy of the messaging directly from an AP if it supports this feature, or from a laptop with an array of wireless network adapters. Some other tools are also useful, such as a handheld instrument, or software that runs on the survey device and works with the survey instrument to gather AP and client device data to help find devices and types and establish initial thresholds and so on. You might also need iPerf software running on the network as the target for iPerf throughput measurements. So this is a heat map. It shows the expected Wi-Fi design measurements for client devices, such as signal strength or the amount of signal above the noise level, the signal-to-noise ratio, with an arbitrary colour scheme and thresholds. These will be different for different clients, so one limitation of heat maps is how well they're calibrated to the target client device. Another limitation of heat maps is that they are totally dependent on the accuracy and granularity of the way in which the survey was taken, or a desktop model was built. If you don't measure losses across walls, or if a wall isn't built into a desktop model, then the heat map will be wrong, because the design tool will project values in the heat map as if the wall wasn't there. More importantly though, it only shows the signals from APs or devices behaving like APs. It does not provide and compare measurements for client devices, which are important for good two-way communication in your Wi-Fi design. Also, roaming measurements are limited to the device on which you're running the Wi-Fi survey when you can connect to the Wi-Fi network, and not the likely different roaming behavior of other non-survey client devices. So, in this building, the APs are set to maximum radio power, and after adjusting for the sensitivity of client devices in the heat map, the signal is excellent. As well as taking measurements for the heat map, a separate roaming test was done with an iPhone moving along the dotted line drawn on the heat map. The message frames between the iPhone and the APs were then captured for analysis with a separate protocol analysis tool. The analysis shows that whilst the iPhone does roam, it does so slowly because it's always receiving a strong signal from its connected AP. And this causes performance problems, which are shown in the protocol analysis on the next slide. This covers the time when the iPhone is connected to AP GF-04 circled in red. So, in the test, the iPhone receives data from a server that is passed through the AP. The options for this connection are for the iPhone to then immediately and implicitly send an acknowledgement to the AP, a block ACK or BA, when it gets a message frame. The iPhone doesn't mandate an acknowledgement to its BAs, so it may send more BAs periodically to make sure that they're received. So the iPhone has a good signal from the AP and it gets a strong frame 133 and replies with its BA. But because the iPhone is a smaller, battery-powered device, it transmits at a lower power level, and when it moves away from the AP struggles to hear its BA. So the AP keeps resending a copy of frame 133 until it hears the acknowledgement. In this case, we see that frame 133 is sent 4 times, and the iPhone sends a BA 8 times before the BA is received, and there's a similar pattern for other frames. So whilst the heat map looks good, it doesn't show the signal strength the AP is getting from the client. The received signal strength from the client should be taken into account so that there's good two-way communication within AP cells, and this is how Wi-Fi needs to be designed. Now, just a note on the power levels seen here. Measurements are usually taken near to the client, but in this case they were measured at the starting point, so the signals are weaker and some of the AP message frames couldn't be decoded. They're missing from the capture and they've been noted manually because we know from the other frames that they're there. If we look at the timestamps around the acknowledgement of message frame 131, we see there are some big gaps, so it's likely there are more lost frames and that the problem is worse. So by taking a range of measurements near the client and taking into account the extra gain that the AP antennas will add to the strength of signals from them, and to the strength that the AP transmits back to them, we can work out the AP radio thresholds. And these can be modelled in the Wi-Fi design tool to work out an optimum design. In the previous example, we saw how the signal strength heat map does not show the signal strength of the client back to the AP. And that suffers when the client roams poorly, especially when the AP signal is strong. In this example, we'll also see that if power levels are not properly tuned, then poor roaming can also affect the signal received by the client, and this is also not obvious from the heat maps. The heat maps above are from a standard Wi-Fi survey which shows the shape of the expected AP cells on the left and the expected signal-to-noise ratio SNR on the right. I've coloured the APs to show how they relate to the cells in the heat map. In this example, the minimum recommended SNR for the design is 25 dB because that will afford the clients a certain minimum data rate. Now, whilst you can do a roaming test with a survey device, the phone, tablet or laptop that you're using to do the survey, by connecting that device to the network under test, you cannot do it for non-survey devices. So additional testing outside the survey software is required to properly understand the effects of roaming for all client devices. Now, whilst the design looked good in the previous heat maps, the actual roaming of the survey device is shown above. We see how the device is holding on to the blue AP cell for too long at the top of the heat map, and at the bottom the light green shows that the client actually attached to an AP not on the heat map because it was in an office on the first floor. The results of the poor roaming choices are shown on the right hand side, and so the required SNR is not met. Once cell size parameters were tuned, we saw the behaviour fall in line with what was expected, and the experience of the client was more consistent overall because of the improved roaming behaviour. As well as using power levels, it's possible to tune cell sizes using minimum basic rates, the minimum rate that APs provide to clients to force them to roam at lower speeds. But in our first example of poor roaming due to high AP power levels, we saw that the data rates were already reasonable, so this might not always work. Also, there are cases where some devices can only work at low rates in some environments, and so this approach would prevent the client from connecting completely, causing serious issues. So client device tests are very important. So to help you understand why Wi-Fi works in this way, and to put it into perspective against traditional wired networking, I've included some slides to explain the basics. If you could see Wi-Fi in a building, it might look something like this. The Wi-Fi devices or access points that provide Wi-Fi services are shown on the ceilings of each floor. Imagine being able to look through the building and see the different radio waves. You would see how radio waves go through walls and ceilings and why they have to be designed in 3 dimensions. APs provide the separate cells of a large cellular Wi-Fi network, and each cell has its own channel or channels based on a radio frequency shown here in different colours. In this diagram, the cells are shown as spheres, but in reality, office AP antennas radiate in a donut shape and will be larger and more irregular. So the picture here is just an analogy. Unlike wired networks, Wi-Fi has to cope with a constantly changing radio environment with any number and type of devices and with the potential for devices to transmit simultaneously. Whilst at the same time, the Wi-Fi needs to be able to deliver the right performance for applications and the capacity for users and their devices. We will see more of performance and capacity later when we look at what makes up data rates in this video. So, Wi-Fi is highly dynamic. It's a cellular network. Each AP operates on its own frequency or channel, and APs advertise services on that channel through Service Set Identifiers, or SSIDs, in separate messages called beacon frames. The client devices, phones, tablets and laptops connect to an SSID that is advertised by an AP. Then the clients roam between AP cells that are delivering the same SSID. And the choice to attach and roam for a service is made by the client device. If you're in computer networking, you'll be familiar with the International Standards Organization ISO, Open Systems Integration OSI, reference model. It breaks computer networking down into 7 parts or layers. These 7 layers were not just a reference model though. OSI standards were produced for implementations at each layer of this model by the late 80s, and although TCP/IP has been adopted as the de facto core networking protocol, other OSI protocols have been adapted or adopted today. The local area network or LAN standards, such as Ethernet IEEE 802.3 and Wi-Fi IEEE 802.11, form the basis of most of our access networks today and are still defined in terms of OSI nomenclature. So modern wired networking courses will cover TCP/IP and the generic LAN standards such as VLANs, spanning tree, link aggregation, and 802.1x access control. And they will touch on Ethernet and Wi-Fi. But as modern Ethernet is switched, providing dedicated paths and predictable performance, a lot of the original complexity to do with the handling of contention and colliding message frames, which the Ethernet standards are designed to deal with, has effectively been removed. Whereas Wi-Fi still has to deal with these complexities in a medium that offers more variables than the early Ethernet networks ever did. So an understanding of how the IEEE 802.11 Wi-Fi standards work is key to understanding how to develop good Wi-Fi. So let's have a look at how you would measure and model different client sensitivities and how the approach has important consequences for accurate capacity modeling. So here we have an access point on the left with its configured radio power. The internal circuitry and cabling reduces the power, resulting in a loss, and the antenna increases the power, resulting in a gain. The transmit power is given as the equivalent isotropically radiated power, or EIRP, the equivalent maximum power of the antenna pattern if it was spherical. As antennas do not transmit perfectly spherically or isotropically, it's taken as the power of the strongest lobe of the antenna pattern. The area of the edge of a sphere is equivalent to the power you're measuring. It drops following an inverse square law of 1 over r squared, where r is the distance from the centre. So the raw receive power level drops by the antenna pattern times 1 over r squared. At the client, the raw receive power then goes through the receive antenna and circuitry, which generally results in an overall gain, but sometimes results in an overall loss. What is measured by the client, the measurements shown in red, reflect the sensitivity of the device. Generally, the best sensitivity would be from a survey instrument with dedicated hardware and special antennas. A laptop with small antennas would have a lower sensitivity, and a mobile device with compromised antennas that are designed to receive signals from all directions and fit into a small space, which is tightly packed next to circuitry, often results in an overall loss. I've drawn a possible example. So the measurements from the survey instrument need to be offset or reduced to show the correct client device experience. Now, desktop designs are usually based on the simulated raw power shown in green. And that means different offsets need to be applied for desktop designs. The main source of noise on a Wi-Fi link comes from interference on the channel, and the greater the difference between the signal strength and the noise, the higher data rates can be. As it's a slightly more complicated topic, towards the end of this video I'll explain how that, provided noise has been taken into account, you can use data rates to estimate client device sensitivity. Noise in a Wi-Fi survey and calibrated for heat map measurements is measured in the survey instrument by calibrated Wi-Fi adapters. But because Wi-Fi adapters are only designed to receive Wi-Fi, they only detect noise by sampling energy levels on the channel between valid Wi-Fi frames to give a rough measure. The cause of any noise needs to be understood and ideally remediated by removing it or avoiding it. A good way to identify noise at specific frequencies is to use a spectrum analyzer. In this example, we have the 2.4 GHz band with 3 distinct 20 MHz wide channels. We can see a couple of noise peaks, but they're just outside the channel envelopes, so it's not a big problem. On the right, we have a radio frequency that's being used, a bit like radar, to detect movement, probably for an alarm or automated lighting. On the left, we have something else, which can be detected across the whole of the floor at different signal strengths. Now, if these were causing problems within our Wi-Fi channels, they would certainly warrant further investigation. Designing for client performance is important because it improves roaming and delivers better communication in both directions between the client and the AP. That's why applying the right client-specific sensitivity measurements is important. The heat map at the top left shows the reported signal-to-noise ratio, SNR, from the survey instrument. But after testing the performance of a barcode scanner and adjusting the sensitivity to match our observations, we see the actual client device experience at the bottom left is much worse. For performance and capacity planning, the expected data rates are also calculated. Used for this are the client SNR sensitivity together with the device specification, which includes the number of spatial streams. The default predicted rates are shown at the top right, but after these have been adjusted to the less sensitive barcode scanner with only one spatial stream, we see that the actual predicted rates are very different. Actual data rates and throughput can be tested for the device running the survey software, a mobile, tablet or laptop, as shown here. But if the devices are not running the survey software, then independent client tests will have to be done to understand how they perform and the rates they achieve. Whilst the data rate heat map shows one data rate range, there are actually different transmit and receive rates, and even these rates vary due to roaming. So the surveyor should drill into the data to understand why there are any differences. As an example, I've made a list of how different key design heat maps are calculated and displayed, and the parameters they rely on. This also shows the problems overlaying measured and simulated elements on the same heat map accurately, and why it's best practice to keep them separate. With the sensitivity adjustments, we need to make sure that there's enough capacity in the combined AP cells provided to deliver the required performance. In this example, we have key parameters for the device specification on the left, the area we are designing for shaded blue in the middle, and the total capacity and client devices and application bandwidth requirements on the right. This example was used to model how a mixture of 5 GHz and dual band 5 and 6 GHz devices might load up the 5 GHz band if they were not operating solely on the 6 GHz band in Wi-Fi 6E networks. It's important to remember when capacity planning that the needs of users are dynamic. They need different things in different places at different times. For example, a number of users might all move into a particular area and all need Wi-Fi at the same time. So capacity is not static and must be designed with these changes in mind. Here is an example of a design that was done for a Wi-Fi first media production company that was having saturation issues with their Wi-Fi. Working with the customer, we were able to determine requirements, thresholds, and ultimately how many cells needed to be built. Then, with a creative use of antennas, it was possible to provide them with the smaller cells needed to deliver capacity and provide clearer boundaries to improve roaming. So in summary, has the target client device been specified and documented? Have client data rates been assessed to quantify the sort of SNR APs and clients are receiving in both directions? Has any noise been assessed, and has a spectrum analysis been taken to understand the impacts of noise on SNR? Have the client device sensitivity offsets been tested, applied and documented differently for both desktop designs and measured surveys? Have the data rates and throughput been modelled and tested, ready for quality and capacity planning? And what capacity planning and testing has been done? So another important area is how accurate and comprehensive are measurements taken during the survey and used in the design. I've seen surveys where only a few measurements have been taken, or some areas missed out completely, and the resulting heat map is then presented to the customer. It's important to survey all relevant areas. If inadequate survey measurements are taken, the survey results will be meaningless. To indicate that the survey has been done correctly, a separate heat map just showing survey paths should be included to demonstrate where measurements have been taken. And mini heat maps should be included to show the measured heat for each AP position across floors. These will be too uniform if they're not measured properly. In the heat map at the top right, we see a number of APs organised in relatively close proximity in a regular grid for a client location tracking design. The signal coverage for the selected AP, which is ringed in blue, is shown. We can see the useful range of the AP in colour and the not so useful range of the AP shown in grey. The grey area will potentially cause contention with other APs on the same channel. The coverage for each AP position is therefore measured right across the floor to record this accurately. If the design extends onto other floors, then measurements on those floors are needed too. However, in the bottom heat map, with inadequate measurements, we see an exaggerated example of how a poor survey can present a picture of good signal strength which just isn't there. Doing an AP on a stick survey like this for each AP or group of APs can be time consuming. So for a hybrid design, only a few comprehensive AP positions need to be measured, then estimates can be made of the effects of wall losses and the expected cell sizes can be properly modelled. Because a hybrid approach allows a lot of modelling, it can be quicker to determine the best design approach, especially when there are a lot of variables to be balanced. But if it's a complicated site, it can also take a long time to build an accurate desktop model too. Wi-Fi thresholds are very small, so they're measured logarithmically, which is also why you have to measure out so far to find the cell boundaries. They're expressed in terms of dBm, decibels with respect to 1 milliwatt, so 0 dBm is 1 milliwatt. In this example, we have a design with a useful cell edge of -67 dBm, and the values may vary depending on your design criteria. But these are of the order of 10 to the -6 milliwatts, which is a small number, and an even smaller number in watts. Some research has shown that a useful BSS colouring cell boundary sits at -75 dBm, which is 10 to the -7 milliwatts, which is an even smaller number. And the physical cell edge, where media contention occurs, is of the order of 10 to the -8 milliwatts, which is an even smaller number. So this gives you an idea of the accuracy required for survey measurements. So you may opt for a hybrid design because it usually saves time and provides more opportunity to model design parameters and alternatives. It's based on a desktop model that models the building and its wall types. It can be based on a series of individual wall attenuation surveys where different wall types are measured so that their RF attenuation or losses can be built into the model of the building. It can also include a small sample of comprehensive AP survey measurements to ensure that the desktop model is producing AP coverage patterns which reflect the survey findings. However, the pattern of the signals from the APs can make it difficult to get accurate wall loss measurements when trying to measure the signal strength on both sides of a wall from an AP to calculate wall losses. The above graph of actual measurements from an AP shows how the signal strength varies with the distance from the AP in meters because of a combination of the antenna pattern and the inverse square losses. It also shows that signals coming out of the AP in different directions, which then get bounced around a room, have different signal strengths, which create a range of signal strength measurements. Close to the AP, at A for example, the natural shape of the signal curve drops sharply, and there are a broad range of signals, B, which will skew measurements when taken on both sides of the wall at distances of a few meters from the AP. Further away from the AP, the signal strength C is much more linear, and whilst there's still a range of values D, they are much smaller. However, walls may be closer than 5 meters from the AP, for example, which may make it impractical to take these readings. There are features in survey software to provide averages for wall types if they're pre-drawn in the software, but this assumes that you've put the right wall types in the right places when you're trying to work out what they are, and it doesn't account for hidden building infrastructure and obstructions such as furniture. So hybrid designs may be based on practical estimates. They may be based on drawings and estimates of standard attenuations for different types of building materials. They may also be tested to ensure that they mirror actual coverage patterns and include examples to demonstrate accuracy. A list of stated assumptions may be included, or they may have stricter thresholds as a margin of error. So once an AP cell has been properly measured or modelled, we'll find areas where cells overlap. Wi-Fi design software can produce a heat map that shows where cells on the same channel overlap, and it's implied that this is bad, but whilst it can be, this is not automatically the case. While cell overlap on the same channel increases contention, because multiple APs are sending beacons on the channel, and the channel is shared by both sets of client devices for the APs, it's handled gracefully by the arbitration process, and it does not necessarily follow that there is channel saturation. In fact, in this example, where it shows lots of overlap in red, these red areas have low channel utilization. Further investigation shows that the red area in the top left is flagged because there's a conferencing system in a boardroom on the floor below that is configured for 80 MHz wide channels and has channel 36 as its primary, whereas all the other APs are on different channels. So in practice there is little traffic, and the conferencing system could be configured to operate on a narrower channel. At the top right, the devices detected were not permanent, perhaps phones that had then been switched off or moved soon after the survey, or possibly in neighbouring premises, and they had little impact in practice on the actual network. In fact, the high utilisation was in the AP cells, where there was no contention, and those AP cells also saw cell saturation issues. Now, it's important to check the detail of high channel utilization in these heat maps because they may include non-Wi-Fi traffic such as interference, and they may include channels that are not being used by the Wi-Fi network at all. But this was not the case here, and the Wi-Fi simply needed more AP cells to deliver more capacity. So, in summary, have plenty of measurements been taken for each AP position, and were they measured out to the cell boundaries? What evidence is there to show the multiple survey paths for each AP in the report, or to include realistic mini heat maps for each AP position? For hybrid designs, how have wall attenuations been estimated or measured, and has there been any comparison with any actual coverage patterns on site? Are cell overlaps reported? If there are cell overlaps, how does the design accommodate them? Or if cell overlaps were discovered during a survey, what is their underlying impact? Similarly, how relevant are channel utilization heat maps? Are they reporting things that are relevant to this network, and what is their impact? So let's now consider client roaming behavior and design. As we've seen, roaming is key to Wi-Fi performance, so we need to understand it and avoid any issues that might happen with roaming. Because roaming adversely affects the performance of static devices and reduces battery life, client device manufacturers deprioritize Wi-Fi roaming in their default configurations, which makes them sticky and slow to roam. Roaming slows transmissions because in order to roam, the client has to go off-channel to discover other APs on other channels it can roam to, and talking to each prospective AP takes time and uses up battery power. On top of that, extra delays are introduced by a regulatory feature of 802.11 called Dynamic Frequency Selection, or DFS. Because Wi-Fi can be used outdoors, DFS requires Wi-Fi devices to wait before transmitting on most 5 GHz channels, because other services, typically radar, may be sharing the channel. Only the first 4 20 MHz wide 5 GHz channels, and more recently the last 5 20 MHz wide 5 GHz channels, are non-DFS for indoor use by Ofcom in the UK, and the more recent change may not be implemented by all client devices. From a roaming point of view, client devices on DFS channels have to first wait for certain valid Wi-Fi frames before they can transmit. Clients need to transmit probe requests to determine the capabilities of APs supporting the current SSID before they can roam. And valid frames on DFS may be a beacon frame for SSID announcements, a probe response requested by another client, or an unsolicited probe response sent out by the AP. It could be up to about 100 milliseconds before a beacon frame is received, and the client has to wait listening on the channel for all that time. Then it has to do the same thing again for every DFS channel it elects to scan. This not only slows down the client, but it also draws a lot more valuable power. To reduce these delays, some client devices may limit the frequency of scans on DFS channels, but that will only slow down roaming. Ideally, a client may obtain a subset of neighbouring channels from its AP as per one of the Wi-Fi amendments, and then it only needs to scan those channels. And if we can avoid DFS channels for roaming, that would be ideal. The implications of DFS for APs are also listed on the slide, and that explains why some channels may not be supported on some APs by some manufacturers. Another delay in roaming is the time it takes the client to authenticate each time it associates with a new AP. This may require an 802.1x authentication followed by an exchange of related keys. Some techniques cache the keys to avoid having to go through the 802.1x mechanism for each association. But in 802.11r, fast roaming, the new client is pre-authenticated with the target AP before roaming, so the client can quickly switch over to the new AP. However, Security measures may prevent fast roaming techniques. For example, change of authorization, COA, allows administrators to change the security policy for users in real time during a connection. If you have COA on in a Cisco Meraki ICE environment, for example, you would not be able to enable fast roaming. Here's a summary of the key 802.11 amendments a client device may support which may speed up roaming. 11K is the standard where a client can request a list of its AP's neighbours or neighbour reports for the client to scan. Some neighbours will be at the opposite side of the AP cell, so they may be out of range, but at least it narrows down the list of contenders. Part of 11V enables unsolicited information about neighbouring APs, SSIDs and channels to be added to beacon frames and probe responses. These reduced neighbour reports are also used a lot in 6 GHz networks. 11R fast roaming pre-authenticates and calculates and shares keys with the target AP prior to roaming to speed up the roaming process, but as mentioned, COA prevents its use. With preferred scanning channels, the standard provides a subset of channels with 80 MHz separations on the 6 GHz band to reduce the number of channels that need to be scanned for roaming. In practice, we don't use 80 MHz channels for enterprise networks in the UK, so this has less immediate value. The way client devices roam is not defined by the 802.11 standard, so different clients will roam in different ways. For roaming choices, clients will usually prioritise signal quality, selecting APs with a good SNR, a wide channel width and plenty of spatial streams. Secondary criteria may be on channel efficiency, preferring 5 GHz versus 2.4 GHz bands and actively monitoring things like the channel utilisation, number of stations and the number of retries, which all flag channel capacity. Tertiary criteria may be a preference for certain amendments to the standards, such as roaming or security amendments. The values for each of those criteria would then typically be graded, for example, into red, amber, green, and one set of criteria may trump another. For example, a good signal quality may trump a poor channel capacity. So because Wi-Fi needs to be designed to optimize client device roaming, we need to do some tests on the client to determine how we can improve it. For example, how long is the client off channel and how long does roaming impact performance? Does it use any roaming amendments and how effective are they? What influences client roaming choices and how can we adapt the Wi-Fi design to improve them? And does the client have any roaming aggressiveness parameters that we can find and tune? The roaming behaviour of clients varies in different situations. For example, on different bands, with different channel widths, with different types and ranges of channels. It's therefore important to test for variables relevant to the design choices of the Wi-Fi design. Testing for 6 GHz is particularly useful, and you can test with different SSIDs, 5 GHz only, dual 5 GHz, 6 GHz, or 6 GHz only. It's important to find out if a client can actually work standalone on 6 GHz or if it relies on a 5 GHz channel to assist roaming. If the client uses roaming mechanisms, do they work properly? For example, 11K may not make a difference with some 6 GHz only implementations. And as mentioned earlier, change of authorization prevents fast roaming. In the example at the top right, a Microsoft Surface sends bad roaming requests with the destination, source and BSSID addresses all equal to the local address. Since this wasn't recognized or responded to by the network, the client can't roam and loses its connection, and this required a bug fix. In another example, when an Android phone was being used for a voice call over a Cisco wireless network, we see that Open 802.1x authentication succeed, but fast roams fail. After one fast roam succeeds, the Open 802.1x authentication stop, but then because the fast roams are not reliable, the connection drops. The issue here is with key management, and further investigation is required to identify the incompatibilities between the client and the network. Once roaming behaviour is understood and the thresholds established, then these need to be incorporated into the design. APs are required in areas where the clients will roam. In this example, that's within the corridors, and the APs provided for roaming are shown circled in red with their roaming coverage. You consider using non-DFS channels for the roaming APs. At the thresholds between rooms and in other areas where clients will move from one AP cell to another, there should be good secondary signal and any other parameters required to facilitate good roaming. One of the things to note is that the configuration needs to be consistent. If some APs have 40 MHz channels whilst others have 20 MHz channels, for example, this may actually skew the roaming algorithm. So in summary then, is the roaming specification of the client device known? Have there been any tests on roaming aggressiveness and roaming efficiency, and can roaming efficiency be tuned? What are the effects on performance of enabling different roaming amendments? Do the amendments work as expected, and if not, why not? How do different bands, including dual band SSIDs, channel choices, channel widths, and other parameters relevant to design choices affect roaming? What cell sizes and Wi-Fi quality measurements work well for client device roaming? What dedicated coverage is provided in the design by roaming APs? And do they deliver the appropriate secondary signal and other quality required to facilitate roaming at the room thresholds in the building where roaming will take place? So let's have a look at how data is encoded over Wi-Fi and understand the implications of SNR for each of them. So this is an example table showing for different types of Wi-Fi the different data rates that can be achieved and the SNR required to achieve them. You can get more comprehensive data rate tables or MCS tables which have SNR calculations for different QAM rates, channel widths and the number of spatial streams, and they can be used to estimate the quality that the client device is receiving, which can then be used to calibrate its offsets. These examples are all data rates for 20 MHz channels. You'll deploy 20 MHz channels when there's a lot of AP cell overlap and you need to keep each AP on a separate channel for performance reasons. If this is not the case, you might use two adjacent 20 MHz channels to form a 40 MHz channel and effectively double the rate on the channel seen here. Each rate here is also based on two spatial streams. Each spatial stream for a 20 MHz channel is sent at the 20 MHz base rate. Two spatial streams then double the base rate, and three spatial streams would treble the base rate, and so on. As data rates increase in QAM modulation, you need more SNR. This is because the different modulations are getting closer to each other and you need plenty of SNR to differentiate them. A similar thing happens as you add more spatial streams, and a separate increase in SNR is required to differentiate the streams. Also, when you double the channel width, you are doubling the total noise across the channel, so you need a separate increase in SNR to compensate for it. SNR values are usually available in the appropriate MCS tables, although there are also formulas to work them out. When taking data rate measurements and when planning capacity, it's important to take into account that as you move away from an AP, so the SNR decreases with the decreased signal strength within that AP cell. So QAM is quadrature amplitude modulation, and it's used to generate a modulation symbol on a subcarrier of a channel. Each symbol is originally a binary number represented using binary voltages. It's then split into two parts, I and Q, and each one is represented as a combined analog voltage. So when I and Q are added as waves, one slightly out of phase from the other, it results in waves of different phase and height, or quadrature and amplitude for each distinct value, that can then be converted back using a similar process. The reason for adding the phase is so that the two I and Q components will not interfere with each other. They are mathematically orthogonal, which makes it easy to extract them back out again. The I and Q voltages for different QAM modulation symbols can be plotted on a graph, known as a constellation diagram. As you can see, as the granularity of QAM increases for higher data rates, so the symbols get closer together, and any noise on the channel could cause an error. This is why extra SNR is required for higher data rates. OFDM simply refers to the modulation that is used across the channel. A number of subcarriers make up the channel, and their frequencies are chosen to be out of phase, again mathematically orthogonal to each other so that they don't interfere. So it's called orthogonal frequency division multiplexing. Each subcarrier provides a QAM modulation symbol, and all the symbols are combined to create one overall OFDM symbol. In this example for 802.11a, there are 48 subcarriers shown in green and 4 pilot carriers shown in red. The pilot carriers are used for phase corrections and timing across the whole of the channel. I've not seen many good high-level explanations of how spatial streams actually work, so I've tried to put a couple of slides together here to do that. Spatial streams take advantage of the fact that a collection of signals following multiple paths from any one antenna at the transmitter to an antenna at the receiver are transformed in a unique way when compared with the transformations between the other antennas. If a client device has 2 antennas and the AP has at least 2 antennas, then the transformations between the antennas provided by the channel can be represented by 2x2 matrices. In linear algebra, the transformation has as many mathematical axes or eigenvectors as the order of the matrices, in this case 2. Because these axes represent a fixed component of the channel, transmissions across these axes are independent and non-interfering, i.e. mathematically orthogonal. Hence they can be used to transmit independent spatial streams. So this is how it works. The cloud in the middle represents the channel, which in turn is represented as a transformation using 2x2 matrices. All transformations can be decomposed into 3 matrices, which effectively represent the overall transformation as a rotation, a stretch, and another rotation over independent axes or eigenvectors. The channel is sounded to work out what the transformation matrices of the channel are for each subcarrier. Then, transmitted data is multiplied by the inverse of matrix VH, so that in effect each stream is multiplied by a vector which aligns it to an independent axis of the channel. Received data is then multiplied by the inverse of matrix U, so that in effect each stream is then extracted back from the channel. The rotations of the subcarriers are cancelled back out, and we're left with the original data plus the noise floor of the channel. That's why, as you add more spatial streams, you need more SNR. Finally, an AP achieves multi-user MIMO using the same approach, but with enhanced processing to eliminate interference from multiple clients. The effects of multipath used for spatial streams don't always help devices. For a single stream device, the effects of multipath look like interference all across the channel or band, which won't show up on a spectrum analyzer. Here we have an example where we have a single stream barcode scanner that cannot be heard by an AP in a warehouse even when it's nearby. We see retransmissions like we've seen before, but in this case the barcode scanner is transmitting at a robust 6 megabits per second, yet it still cannot be heard. Default recommendations by the survey software to increase minimum basic rates would only exacerbate the problem. We might be able to diagnose that this is being caused by multipath in the environment by taking the client out of the warehouse to an office with its own AP and observe the data rates there. Additional mechanisms can be used to improve the reception of the encoded spatial streams. One is space-time block coding, where an additional matrix transformation is applied to the spatial stream transformation to provide redundant copies of the signal, which ensure that a receiver with additional antennas receives at least one good copy of the signal. Another is transmit beamforming, where the phase of signals from different antennas is tuned so that they arrive constructively at the receiver's antennas. Combining spatial streams, STBC and transmit beamforming each require additional antennas, so they're normally provided by the AP depending on the number of antennas. But it's possible for a client with 2 antennas to drop the spatial streams and use either STBC or transmit beamforming to improve its signal to the AP. So depending on the specification and features of a client, it may be possible to use these enhancements to improve an AP's reception of weak client signals, which would be one of the more useful use cases for these technologies. One final thing that will affect signal strength is polarization. So polarization should be tested during the client device evaluation, because if the client device or AP have only one polarization state, there could be performance and compatibility issues. It's generally not seen as a big problem in most scenarios because modern APs with at least 2 antennas are cross-polarized. The horizontal and vertical components of any signal are therefore transmitted and detected by both horizontal and vertical polarized antennas. Now, if you have a device that has only one polarization state, then you need to understand how polarization changes may affect it. Whilst reflections of a perfect conductor, such as metal, retain the polarization state, reflections bouncing around metallic corners could actually change it. Also, reflections off any non-conducting, non-metallic material, such as a concrete floor or a plaster wall, would change the horizontal and vertical components. Now, polarization is most likely to be a problem for a client with only one antenna, because it's most likely to have only one polarization state. But it's best to check all devices just in case. So just a quick recap. So here's a list of things to check for client sensitivity and capacity, updated with a little more detail. And the things to check about measurements in your Wi-Fi survey. And the things to check about roaming in your Wi-Fi survey. So to finish, are you just presented with some generic or automated heat maps without any explanation, commentary or application of knowledge of the relevant aspects of Wi-Fi? Is there a summary of findings? If config recommendations from the survey tool are included, is there evidence of them being tested and qualified, or are they just being copied into the report verbatim? You've paid for the Wi-Fi survey, so you need to check it's been done properly and that you're getting value for money.